Hey everybody, I wanted to go over with you a little bit more in depth with the data analysis component of the Spec 20 lab now that you have gone through and kind of collected some of the data through the simulation and actually made the graphs and kind of saw what they look like. So I want to show you kind of how we can use those graphs to actually calculate some things about our solutions that we run tests on. So when you get data from a Spec 20, the data that you typically get depends on the type of machine you get. The newer machines give you absorbances right away, but the ones we have right now are a little bit more low tech and they give us transmittance. And so if you were to graph transmittance versus your molarity, regardless of the type of solution you made, you would get a graph that looks kind of like this. It's got more of an exponential shape to it than a nice straight line. And that's because when we talk about transmittance data, transmittance is kind of an exponential function. When I made this graph, this was for a solution of copper 2 nitrate that I was using. And if you look, the data at least kind of makes sense that the higher the transmittance, the lower the molarity is. But like I said, we've got more of a curve here. And if you look at the linear regression that I put in, the R squared value is 0.942, which is not a particularly good R squared value. We're looking for a value close to 1 if we have a line that's, going to be working really well for us. So this data is not super useful for us because we can't necessarily put a trend line in there or a linear regression to use that. So if we would have had just gotten transmittance data, you would have had to run through the calculations and actually calculate the absorbance value. And then using this same data, you would have gotten this particular plot here. Now, this is what we call a Beer's law plot because Beer's law ties together absorbance and molarity. So absorbance is on your Y and then molarity is on your X axis. And so this will be our Beer's plot in this case for copper nitrate. And the optimal wavelength for the copper nitrate turned out to be 620 nanometers. So here, if you look, I have a much more linear trend to my data, and I forgot to put the R squared value on here, but I can tell you it's definitely much more close to 1 than our previous graph was. In this particular graph, I got a linear equation as well. And so when we talk about our linear equations with these plots, you can calculate the absorbance or molarity using this equation here. In your equation, your Y value is going to be your absorbance and your X value is going to be the molarity for your particular solution that you have. And then it's just a matter of kind of solving this. If you are given a graph on the AP exam, and I have seen this where you aren't given this equation, you can calculate the slope value by doing a rise over run calculation and then putting that in for your slope. If you think about the units on this, absorbance is a unitless value, so Y is going to have no units on here. X comes from our molarity, so in this case, it's going to be X is moles per liter. And then here for our y-intercept, again, is unitless. So the slope value here needs to actually cancel out the molarity. So the units on our slope in this case are 1 over moles per liter or 1 over molar to complete our calculations. So I want to walk you through an example calculation if we're going to be doing a graph calculation, like let's say you have a linear regression. So here is our first calculation. Using your graph, what would you expect the absorbance of a 0.18 molar copper nitrate solution to be? So I'm going to have you guys pause the video and I want you to use that equation from the previous slide. Can kind of zip back in the video and then try to calculate that out. And I will work through that with you in just a minute. All right, we're going to switch over to my handy dandy doc cam, and then we are going to work through this question together. So in my graph, my equation was y equals 1.7102, x plus 0.0287 for my y-intercept. So like I said, we have kind of a couple different values here. My y is going to be my absorbance because that's how my graph was made. My X is going to be, in this case, molarity, moles per liter. And then this y-intercept is absorbance and has no units. Okay, this guy doesn't have any units, and so my slope here is just going to be rise over run. So the rise is nothing, the run is moles per liter. So my units on my slope are 1 over molar, you could write. You could also write liters over moles, or you could write molar to the -1. All of those are appropriate for when we are solving this problem. So the problem is telling me that I have a 0.18 molar solution of copper nitrate, and I want to find my absorbance. So when I use my equation, I need to put the molarity into where the molarity belongs, and that's in the case of X here. So I'm going to solve for Y, and that's going to equal 1.7102. Remember, the units on this guy are molar to the -1, or 1 over molar, or whatever works for you, times 0.18 molar. Now, these units then can cancel each other out, plus 0.0287, and that's unitless because absorbance has no units. When I put this into my calculator, I'm going to multiply these first and then add this, and I should get a absorbance value of 0.336. Now, it's always good to go back and check and see if this makes sense for our graph value. So let's go back and check it out. And if you look here, if we would have had a value of about 0.18 and we go up and look for the intersection of that line, we aren't quite to the 0.35 value. So, hey, that makes sense. Congrats. Okay, now, like I had talked about in the previous slide presentation, Beer's law, what it does is it basically takes that linear regression and puts it into an equation. So Beer's law states that absorbance is equal to epsilon times B times C. And epsilon is something called the molar absorptivity constant. To get the molar absorptivity constant, it's unique to every chemical that you test. So like if I'm doing a nickel solution versus a copper sulfate versus a potassium permanganate solution, that molar absorptivity constant is going to be different for each value. And when you do your plot of absorbance versus concentration, the slope that you get is usually your molar absorptivity constant, as long as you have a 1 centimeter path length or a 1 centimeter cuvette in your Spec 20 or your spectrophotometer. So realistically, the molar absorptivity constant is that slope value divided by the path length, but 99% of the time, the path length is going to be 1 centimeter. So all it does is it adds a centimeter component to the unit, and I'll show you that in a second. B is the path length for the solution. So that is how wide your cuvette is. Like I said, most of the time, that's going to end up being a 1 centimeter path length. And then C is the concentration of the solution. Now, we're typically going to be using moles per liter, but it could be anything. As long as the concentration is the graph and the slope is made in a specific concentration, you can kind of solve for anything. So just be conscientious of the units that are on that slope when you are solving for any given problem. In ours, it was moles per liter, so we're going to use moles per liter. Okay, so like I said, with the calibration curve, then we can turn this law and our graph into an equation. So here is our example. Using Beer's law, what would you expect the molarity of a copper nitrate solution to be if it had an absorbance of 0.61 and a path length of 1 centimeter? On this problem, I would like you to use the slope of our line as our molar absorptivity constant. So please look back and find that slope, and then we're going to try and do that calculation. So pause the video, get that absorptivity constant, and then we'll take a look at this problem too. All right, let me get my doc cam back up. All right, so here is our second question. Using Beer's law, what would you expect the molarity of a copper nitrate solution to be if it had an absorbance of 0.61 and a path length of 1 centimeter? So Beer's law tells me that the absorbance is equal to that epsilon value times my path length times my concentration. And again, I've told you before that absorbance has no units. So when you think about this as kind of an algebra problem, all the units here need to knock each other out to give me nothing left over for units at the end. If you look back at our slope here, the slope was 1.7102 for its value. And the units on that for the actual slope originally were, I'll write like over molar here, or you could write molar to the -1. But when we take into consideration the path length, we add a unit on the bottom as well. So we divide this by our path length. Since our path length is 1 centimeter, it's just going to be the same number. If you wanted to write this as 1.7102 molar to the -1 centimeter to the -1, that would be fine too. Now my path length is going to be 1 centimeter, and I'm looking for my concentration. So when I put this into my equation, I'm going to have 0.61 equaling 1.7102. And then I'm going to write it as over molar centimeters. If you like this way better, you're fine doing that too. Then we are going to multiply it by the path length, which is 1 centimeter. And here's the reason why I like this, is because then my units are on top and bottom and they cancel out. But you got to be careful. And then I do not know what my concentration is, so I'm going to solve for C. Now, do not put units on here. You're going to use your math to make sure that the units work out. Now, in this case, I need to get my concentration by itself. So I'm going to divide both sides by 1.7102 over molar. Okay, so what's going to happen is my math is going to be the 0.61 divided by 1.72, and the units in this case, because it's 1 divided by 1 over molar, these molar units will flip to the top here, and then we will see them show up, which is what we want them to do. So if I take this and divide the two of them, my concentration value ends up coming out to be 0.357 molar. So if you think about it, that kind of makes sense. If I have a higher absorbance, I'm going to have a higher molarity than I did in my previous problem. Now, you might say to yourself, why is this path length thing important? So if I have a 1 centimeter path length for my light to travel through, when I take that reading, if we say this is all my light and this is light that passes through, when we take that reading, we get our percent transmittance. Okay. If I, let's say, take this cuvette and I squish it down and I have the same concentration solution now, I'm going to divide this out so we don't get confused, and I send the same amount of light through, if my cuvette this time is only 0.5 centimeter long, I'm going to end up having more light pass through. And the reason for it is that absorbance and transmittance are related literally to the number of particles in this solution. So if I don't have any more particles, or I have fewer particles than I did before because my cuvette is only 1/2 the thickness, I am going to get not as much traveling or not as much absorbed because there's just not as many particles to kind of capture this light. So in this case, I'm going to have a higher percent transmittance. However, when I take a look and I take into account my path length, the absorbance will end up coming out to be the same because I've got this shorter path length when I talk about Beer's law. Okay, so when I use my linear equation, I'll get a different slope value, but it'll still work out the same because I'll have that same linear relationship. In contrast, if I stretch this cuvette out, I'm going to have less light getting through at the end here because I'm going to have more particles that can trap the light. Okay, so when we're talking about adjusting path length, you're going to want to take into account this value here, this equation, because it's going to help us find our concentrations. So again, keep these things in mind, and if you have any questions as you're going through your lab, please let me know. All right, good luck.